So what does Bohm add to the standard quantum descriptions? You all know. In a word, the particles themselves. For Bohm, the so-called hidden variables are simply the positions of the particles of the quantum system, say the electrons of an atom. These particles move in a manner which is naturally choreographed by the wave function of the system. From the perspective of Bohm's theory, orthodox quantum mechanics leaves out the guts of the description, the very particles which combine to form everything we see around us. Thus, as applied to Bohm's theory, the terminology hidden variables seems rather inappropriate, suggesting as it does something exotic, artificial, and ad hoc. Here's Bell. Absurdly, such theories are known as hidden variable theories. Absurdly, for there, in these theories, it is not in the wave function that one finds an image of the visible world and the results of experiments, but in the complementary hidden, quotes and an exclamation point, variables. Of course, the extra variables are not confined to the visible macroscopic scale, for no sharp definition of such a scale could be made. The microscopic aspect of the complementary variables is indeed hidden from us. Here Bell refers to the fact that in Bohm's theory, the detailed trajectories of the microscopic particles are not observable. While this unobservability is a consequence of the very structure of the theory, many physicists quickly objected. After all, physics is about prediction, about observation, not about things which cannot be observed, so they say, so that many would say. Here's Bell. But to admit things not visible to the gross creatures that we are is, in my opinion, to show a decent humility and not just a lamentable addiction to metaphysics. The very existence of Bohm's theory, agreeing as it did in its predictions with those of orthodox quantum theory, quite naturally under the circumstances, raised many questions for Bell. But why then had Born not told me of this pilot wave, if only to point out what was wrong with it? Why did von Neumann not consider it? More extraordinarily, why did people go on producing impossibility proofs after 1952, when Bohm's theory was published, and as recently as 1978, when even Pauli, Rosenfeld, and Heisenberg could produce no more devastating criticism of Bohm's version than to brand it as metaphysical and ideological? Why is the pilot wave picture ignored in textbooks? Should it not be taught, not as the only way, but as an antidote to the prevailing complacency, to show us that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice? Of course, the most immediate question raised was, or should have been, what went wrong with the proof? All of the impossibility proofs, von Neumann's in particular. And I won't read this again because I read it at the beginning, the realization about the limited relevance of von Neumann's proof. I'll skip that. Well, Bell analyzed von Neumann's proof as well as other proofs, found that they were based upon rather arbitrary assumptions or axioms, and focused on the manner in which Bohm's theory violated these assumptions. And in so doing, he noticed that what I read before, there's an explicit causal mechanism. His investigation of that led to Bell's inequality. No sooner said than done. No sooner did he raise the question of whether he could do better and rule out and find an impossibility proofs for at least local hidden variables. He did it, and he got more than he bargained for. No sooner said than done. In fact, if we follow the publications date, done before said, the EPR Bell's theorem paper, 1964, in which it was done, appeared almost 2 years before the paper from which I was just quoting about, which led to this. There was publication delay. Bell interview. As a professional theoretical physicist, I like the Bohm theory because it is sharp mathematics. I have there a model of the world in sharp mathematical terms that has this non-local feature. So when I first realized that, I asked, is that inevitable, or could somebody smarter than Bohm have done it differently and avoided this non-locality? That is the problem that the theorem is addressed to. The theorem says no. Even if you are smarter than Bohm, you will not get rid of non-locality. That any sharp mathematical formulation of what is going on will have that non-locality. Moreover, the non-locality of Bohm's theory derives solely from the non-locality built into the structure of standard quantum theory as provided by a wave function on configuration space, an abstraction which, roughly speaking, combines or binds distant particles into a single irreducible reality. Here's Bell. That the guiding wave, in the general case, propagates not in ordinary three-space, but in a multidimensional configuration space, is the origin of the notorious non-locality of quantum mechanics. It is a merit of the de Broglie-Bohm version to bring this out so explicitly that it cannot be ignored. Now the relevant experiments have been done, confirming the strange predictions to which Bell was led by his analysis of Bohm's theory. Where does this now leave us? There's a basic problem. Bohm's theory violates Lorentz invariance, a central principle of physics. Nor can Bohm's theory be easily modified so that it becomes Lorentz invariant. The difficulty here arises from the fundamental tension, the apparent incompatibility between non-locality and Lorentz invariance. Bell interview. Now, what is wrong with this theory, with David's theory? What is wrong with this theory is that it is not Lorentz invariant. That's a very technical thing. And most philosophers don't bother with Lorentz invariance. And in elementary quantum mechanics books, the paradoxes that are presented have nothing to do with Lorentz invariance. Those paradoxes are simply disposed of by the 1952 theory of Bohm, leaving as the question of Lorentz invariance. So one of my missions in life is to get people to see that if they want to talk about the problems of quantum mechanics, the real problems of quantum mechanics, they must be talking about Lorentz invariance. And from the last sentence of, to my knowledge, Bell's last publication, the last word, as it were, referring to Bohm's theory and to GRW theory, which you've heard about, a modification of quantum theory in which he became interested in his last years, Bell said, the big question, in my opinion, is which, if either of these two precise pictures, can be redeveloped in a Lorentz invariant way. I believe that this really is the big question, and I urge it upon you. But I am afraid that in trying to answer this question, we shall miss Bell's help and inspiration very much indeed. And we shall miss Bell's marvelous style, his penetrating wit, and his brilliant clarity. Thank you.